nanohub.org.
What we're going to move towards today is, number one, we're going to first look at what difference in everything we understand so far happens when you take into account the fact that the cantilever is oscillating in an eigenmode. And so the shape in which it oscillates is not going to be the simple bent-tip shape, but it could be a wigglier shape depending on what eigenmode you choose. What difference does it make to the point mass oscillator model? That's number one. Second thing we'll switch to is we're going to talk about analytical approaches. You've done Veda, which is, detailed numerical simulations with everything included. But at some point, it's nice to have closed-form analytical solutions to things, right? And so there are analytical approaches to things. We'll talk about an analytical approach today that is the basis for phase contrast imaging, okay? So we'll segue to analytical approaches, phase contrast. It's an extremely important lecture, and I hope you sink your teeth into it and really get to understand the details, okay? All right. So remember that when we did all our modeling of cantilevers, we simply had a tip. We modeled the cantilever as a spring with a spring constant, and we just had a tip at the end of it. In reality, what happens is if you take a cantilever and you do a frequency tuning, at certain specific frequencies, you hit a resonance, the amplitude increases. When it does hit a resonance, it shakes or oscillates in a very characteristic shape. Okay, so if you took a normal AFM cantilever and you swept up the frequency, the first drive frequency at which you get large amplitude motion is the first resonance, right? And we basically get large amplitude motions whenever your drive frequency equals natural frequency, okay? So what ends up happening is when you start increasing the frequency, excitation frequency, you're going to hit a frequency at which the first eigenmode starts resonating. You get large amplitude motions, yeah? And there's a characteristic shape associated with it. You can see that if you took a sort of snapshot of this, you would, let me just run it in a loop so you see this better. It should loop, hopefully. Yeah. So now it's looping. So it's oscillating up and down, and it's got a certain shape. But if you look at the overall shape, it's the same. It's just its magnitude is changing with time, right? It's the same shape basically. So that's what it'll oscillate at when you're at the first natural frequency of the cantilever. As you start increasing the drive frequency above this, what happens is the amplitude becomes small again because you're no longer at resonance. You keep increasing the excitation frequency, keep increasing it until you hit another characteristic frequency corresponding to the second eigenmode. And then suddenly you start getting large amplitude motions again, and that corresponds to the second eigenmode, which looks like this. Okay? And then it's shaking a lot, right? It's oscillating a lot. And then you increase the drive frequency a little more past resonance, and you're off resonance, so nothing moves again, right? And you keep increasing frequency until you go to another characteristic frequency where suddenly the amplitude becomes large and it starts resonating in a yet more complicated fashion, okay? And actually, if you look at it, there are many characteristic resonance peaks as you shake, right? Each corresponds to a particular motion of the cantilever. You can also get certain characteristic frequencies at which, when you drive it at those frequencies, it oscillates, it flaps back and forth like in a torsional mode, okay? This would be the first torsional mode. This would be the second torsional mode, which happens at even greater frequency, and then you get, the third torsional mode, which is at really high frequency. So the point is that when you've got a cantilever and you do a tuning curve, if you do a tuning curve over sufficiently long frequency range, let's say up to 1 megahertz or 2 megahertz, you'll find many peaks. This is in air, and you choose one. When you choose one, the cantilever tends to oscillate in one of these shapes. You choose another, it oscillates in the next shape. You choose another frequency, it oscillates in a different shape, okay? So it's very clear that depending on which peak you choose, the shape of the cantilever as it oscillates is different. It's not simply going to be this nice cubic curve that we get when you apply a point force at the end. It's not that simple shape, okay? It can be a very complicated shape. So how do we begin to understand this? By the way, all this is real experimental data. How this is done is you take your cantilever chip and shake it with a piezo, but observe it under what's called a laser Doppler vibrometer, which makes a grid of points on the cantilever, scans the vibration response at every point of the whole thing, and so you get a full field information of displacement. So the colors are actually proportional to the actual displacement at that point. So it animates that basically at those frequencies. So the lowest frequency mode is shown on the top left. This is what's called the fundamental mode of the cantilever, and that's the number that's always quoted on the box of chips you buy. It tells you what the fundamental frequency is, and if you drive the cantilever and near that frequency, near that resonance, you get a motion like that. But as I said, if you do a tuning curve over a much larger frequency range, 2 megahertz, you'll see many peaks. And you can choose a peak corresponding to the second mode. You can choose a peak corresponding to the third mode. Of course, it's not very easy to figure out as you go through beyond the fundamental. It's not very easy to figure out. You just see a peak, but what you don't know is exactly what kind of motion it corresponds to. It's hard to know, right? Unless you do some sort of an analysis to figure out that, well, the first mode is this, as the next higher frequency is actually the second bending mode and not the torsion mode. So you need to have some idea when you use these higher modes, which peak corresponds to which mode shape. It's not the easiest to figure out, okay? So it helps to have some background, to do some analytical modeling of these eigenmodes to understand which one is which. Just to recall, when we did the point mass model, what we basically said is that the tip is like the mass, and the cantilever acts as a spring, right? With a spring constant given by the static spring constant, right? But that assumption, if you think about it, if we say that this cantilever acts only as a spring, right, implies that you're neglecting the mass of the cantilever. You're just saying basically the tip is there and the tip is suspended by a spring. So that means you've completely neglected the mass. You represented the cantilever as a spring and you've forgotten about its inertia. When in reality, the cantilever mass is actually much more than the tip mass. Much more than the tip mass, right? Usually the cantilever mass may be 20, 30, 40 times that of the tip mass. Maybe 50 times. So the whole idea that you can just forget about cantilever mass is not a very good idea. So we do need to worry about that when we really take into account the fact that, the cantilever beam is a continuous medium that's flexing and oscillating, right? The second thing is, in our previous analysis, when we did the point mass model, we simply put in the spring constant K as the static spring constant of the cantilever, which is when you apply a point force, what's the resistance you feel, right? So that stiffness is what we use. In reality, as you've seen, depending on the eigenmode you choose, the shape in which the cantilever oscillates is not given by that simple cubic relation, as a function of distance, the cubic curve that represents the centerline displacement if you applied a point force at the end of the cantilever. It's not like that, which means everything we know about what should be the stiffness of that spring is out of the window, right? You need to understand the shape in which it oscillates to really know what spring constant number to put into the point mass model. So clearly, when you start dealing with a cantilever now as a continuous structure which flexes and twists and all these things, it introduces a lot more complexity than the elegance of the simple point mass model. We all like point mass models because it makes life simple. On the other hand, this complicated three-dimensional structure of this beam, how can we sort of compromise this? How can we take this complicated structure and yet represent it by a single point mass model? That's another thing we would like to retain. So I guess the point is we're going to make life a little more complex by studying the exact shapes of these eigenmodes, but we're going to come back down to a point mass model later, okay? But except we're going to use what's called the correct point mass model, which means It'll be a point mass model, but where the spring constant is the true spring constant corresponding to that given eigenmode shape, and so on. So we'll come back to that to make life easy, okay? Okay, so let's go back to simple beam theory, and we're not going to worry about torsional modes. We're just going to study bending modes as this beam flexes and bends. And you've already seen our basic equations that we used for this before when we did the static analysis, right? You remember? We derived equations for when you have a point force at the end of beam, how does it bend? We derived equations for when the force is uniformly distributed on the beam, how does it bend, and so on. The only thing we need to include now is inertia of the cantilever, because it's oscillating, right? So you need to include inertia term. How do we include the inertia term? Well, on the top left, you see a sketch of a beam that's, it's a snapshot as it's oscillating, so that the centerline deflection W is a function of spatial coordinate X and time both now, all right? Q corresponds to the motion at the tip, up and down motion at the tip specifically, okay? Now, what we do is we take a section at a distance x, so we make a virtual slice through this beam at a distance x, as shown, and we make another slice at x plus delta x. So this little rectangle you see is basically, if you will, you've made a slice through the cross-section at x, another slice through the cross-section at x plus delta x. You got two open faces, if you will. On the left-hand side, you got the shear force Vx and the bending moment. We've done all this when we did static bending analysis. It's the same thing, no difference. And then you have the bending moment and the shear force on the right-hand side, and you have the external load Px acting on that little sliver, right? Nothing changes. The only thing is, when we did this analysis last time, what we did is, we did not include inertia of this little wedge as it moved up and down. So in which case, all we had to do was sum of forces equals 0. So when we did this analysis previously, we just said that all the forces, vertical forces, must sum up to 0 because it's in equilibrium. Well, now, it's not in equilibrium, it's accelerating. So the sum of forces is going to be equal to the acceleration, mass times acceleration, Newton's law, okay? That's the only difference we have to do. So when we take that into account, what you basically get is the equation on the top right, which is rho a w double dot. This is the acceleration of the, so if you take rho a w double dot and you multiply it by dx, delta x, the thickness of this wedge, that gives you the acceleration of this wedge. Why? Because if you look at what the mass of this little wedge is going to be, the mass of this little wedge is going to be rho, which is the mass density, times the area of cross-section A, rho A, times delta x, okay? So that is basically density times volume. That gives you the mass of the element. Rho A delta x is the mass of the element. So rho A delta x times the acceleration is w double dot. That's going to be the vertical acceleration. So if you look at the equation on the top, as delta x tends to 0, what you simply get out of it is, so the balance of forces is shown on the very top, Vx plus P xt delta x minus Vx delta x. This total vertical forces must equal mass times acceleration. Okay, that's the very top equation. You take the limit as delta x goes to 0, and you now define the derivatives, and you get rho a w double dot equaling negative partial v partial x plus the external load, whatever there is on the beam. Okay, distributed load on the beam. Now, we derived a relationship, several lectures ago, that connected the shear force partial v partial x to the bending moment. Okay, so partial v partial x is actually second derivative of bending moment m, partial x squared. And the bending moment, in turn, we derived a long time ago, again, is simply the elastic modulus E times the area moment I times the second derivative of, or times the curvature of the beam, effectively. So the equation of motion we get is actually shown here. Rho a w double dot plus EI, fourth derivative w with respect to x squared equals px comma t. The only difference of this compared to what you did before is this acceleration term, rho a w double dot, right? That's the only additional term, is the ma term, the acceleration term, okay? But now what this does is that It seems a very simple term to add, but what it has done is it's converted the problem from an ordinary differential equation into a partial differential equation. Because when we solved for what's the shape of a beam when you apply a static load, there was no time dependent. The equation was only along x. So it was an ODE with boundary conditions. Now you have time, so it becomes a PDE with boundary conditions and initial conditions. Okay? So simple, but at the same time, now we're getting to a PDE effectively. Okay? Now, it has to be solved with boundary conditions, and typically the boundary conditions are deflection on the far left at x equal to 0 is going to be 0 because it's going to be fixed, clamped, if you will, to the chip, right? And you want to have the slope equal to 0, right, at x equal to 0. So right now, what we look at here is going to be what I call free vibrations, okay, which means let's not for the moment worry about shaking the base. Let's not worry about applying a magnetic field to shake it. We just look at what are the characteristic frequencies and what are the shapes in which they vibrate in, for which you do not need to include any forcing. You just look at naturally what are the natural frequencies and what are the shapes, characteristic shapes in which the beam wants to vibrate in, okay? So we put those boundary conditions. We need boundary conditions at x equal to L, which is the far end of the cantilever. At x equal to L, there's a shear force and there's a bending moment. And I'll put question marks here to ask you the question, what should be the shear force at x equal to L, and what should be the bending moment at x equal to L? And it's not an easy question, right? It is a slightly tricky question because after all, this entire equation of motion I wrote down was for the beam, not for the tip, right? So if we want to include the effect of the tip in some sense, it would have to come into the boundary conditions at x equal to L, right? Because so far the equation is just for a beam, not for a tip, not for a little sharp conical tip at the end. So if you really want to do this, if you want to include the effect of tip, so if you just set this equal to 0 on the right-hand side, you're basically saying that the mass of the tip is negligible, right? So that really what should happen is this shear force should equal mass times acceleration of the tip. That's what you should get. Like the force at the end of the beam should equal mass times acceleration of the tip. So if you set it equal to 0, you're effectively saying the mass of the tip is basically 0. And for the most part, that's not a bad assumption because the mass of the tip is usually 10%, maybe 5% that of the mass of the cantilever. Maybe you can neglect it, but we'll discuss today that often you can't neglect it, okay? So anyhow, I've left this as a question mark. In the classical analysis, you would neglect the tip mass completely, which is, if you think about it, the complete opposite of what the point mass model does. In point mass model, you neglect the mass of the entire beam and just worry about the tip. Here, if you just set these things to 0 on the right-hand side, you're neglecting the mass of the tip completely, okay? If you want to be precise, you start including here mass of the tip times the acceleration of the tip. If you want to be precise here, you want to include moment of inertia of the tip times angular acceleration of the tip, right? Because the moment at the end of the beam must equal moment of inertia times angular acceleration of the tip. So those are boundary conditions you could include if you wanted to get fancy and really worry about how the tip is affecting the dynamics. But 99% of the cases, people just set this equal to 0, which, as it turns out, is fine as long as you're dealing with the fundamental mode, okay? Okay, so let us take the simple problem and set it equal to 0 on the other side, okay? So we neglect tip mass completely. What do we do beyond that? So the equation we have at hand is equation 1. We're trying to solve this equation 1 to get what the natural frequencies are and what the characteristic mode shapes or the shapes associated with those resonances are. The first thing is a PDE involving time and space x. So we do a separation of variables. Equation 2, we write W as a product of a function in x times a function in time. And plug it in and rearrange, and we get equation 3. On the left-hand side, you will notice we have a function of x, right? So we rearranged it so the term on the left-hand side is only a function of x, correct? The term that depends on time is only a function of time. And so the only way that that they can be equal to each other is if they're actually constants, right? So the only way a function of x can be a function of time is if they're both constants. So we equate it to a constant, and we just give the constant a certain value, omega squared. That's equation 3. All right? So now we actually have two equations. We have this function of time, 1 over t times d squared t dt squared. That must equal the constant. That's one equation. And then the second equation we have is this one, ei over rho a, this function of x. That must also equal the constant. That's another equation. So we got two equations. If you look at the right-hand side of equation 3, the equation time, which is 1 over t times d squared t dt squared equals this constant omega squared. If you want to solve that equation, the solution to that equation is simply the function of time, t, uppercase t is a function of t, is simply going to be harmonics in omega t, with frequency omega. A sine omega t plus b cosine omega t. So if you think about it, this general solution, a sine omega t plus b cosine omega t, satisfies the time, the equation in the differential equation in time. Okay? Because remember, the differential equation in time is simply second derivative of this function t with time must equal negative omega squared. So that means this function t can either be sine omega t or cosine omega t. Because two derivatives of sine omega t give you negative omega squared, right? Two derivative of cosine gives you negative omega squared also. So in general, the solution uppercase t is going to be a cosine omega t plus b sine omega t, okay? Or a sine plus b cosine. So that part is easy. Let's look at the equation corresponding to the space-dependent part, where we have this fourth derivative of phi term must equal this constant omega squared. What's the fourth derivative? So you have to approach it slightly. You can't just say the solution is going to be sine and cosine, all right? So the general approach is to write phi of x as some c e to the lambda x, where our goal is now to figure out what the lambdas are. Right? They're the characteristic multipliers of this boundary value problem. So we plug in equation 4, the form equation 4 into 3, and we find out what the lambdas are, right? And we get the lambda 1 comma 2 must equal plus minus beta. Beta is basically omega squared, okay? So it's beta is related to omega. And lambda 3 comma 4 is plus minus I beta, which means that the general solution phi of x must include c1 e to the beta x minus beta x, e to the I beta, e to the minus I beta. Okay, because there are 4 values of possible lambdas. So the most general solution for phi must be a superposition of e to the lambdas, lambda 1, lambda 2, lambda 3, lambda 4. Okay? Now, there's a simple identity which says that if you've got something which is a superposition of terms involving e to the x's and e to the I x's, it is equivalent to having a superposition in terms of sine x's and sine hyperbolics and cosines. Because e to the ix plus e to the minus ix divided by 2 is connected to cosine hyperbolics and so on. So it's basically equivalent to writing that phi of x is written in terms of sines and cosine hyperbolics of beta times x, beta involving the natural frequency omegas, okay? So we are at this point, and this whole analysis is now going to tell us what are the different omegas and what are the different shapes of the corresponding eigenmodes, okay? How do we do that? This is where now we go into the boundary conditions, okay? And so we're going to do the simple boundary condition, which is to say that the tip mass is 0. So on the left-hand side, where the beam is clamped, the W 0 is 0, which the deflection is 0. The slope is going to be 0 since it's flush, it's sitting, you know, there's no bending slope. So on the right-hand side, we neglect tip mass. As I said, this is an approximation. There are issues with this. But let's neglect it, which means that the shear force and bending moment need to be 0 at the free end. All right? So our general shape of the eigenmode is shown on the top, C1, cosine, cosine, sine, and hyperbolics. We're trying to determine these four constants, C1 through C4. If we determine them, we're determining a characteristic shape, okay, corresponding to it. So we plug in these boundary conditions, and we plug in that expression 1 into these boundary conditions, and we get from the first two boundary conditions, we find out that C1 and C3 must be 0 in order to satisfy the first two boundary conditions, okay? So now we're left to try and determine what the constants C2 and C4 are, for which we go to the latter two boundary conditions. We put in those expressions at x equal to L, and we rearrange. We're trying to determine C2 and C4, and effectively what we get is equation 3. There's a right-hand side is missing. It should be equal to 0, okay? So really what you have is this matrix times C2, C4 equals 0. And we got two equations. We're trying to solve for C2 and C4. Now, keep in mind that the right-hand side of equation 3 is equal to 0. So if the right-hand side is equal to 0, C2 and C4 are going to be 0. Okay? So we don't want C2 and C4 to be 0, because C2 and C4 are 0, there is no shape. Then all the constants are 0 and phi is 0. There's no characteristic shape. So we cannot have C2 and C4 equal to 0. The only possibility where you have a matrix equation equaling 0 and wanting C2 and C4 not equal to 0 is the only situation that's possible is if the matrix is actually singular, which means its determinant is 0. This is basic linear algebra. Okay? So the only way we can get some characteristic eigenmode shape is going to be to set the determinant of this matrix equal to 0. And as we do that, we get equation 4. Equation 4 basically is the statement of the fact that the determinant of that matrix is 0. Okay? And now we're talking, because it turns out, remember, beta, what is beta? If you go back one slide, beta is simply related to omega squared times this rho, mass density of the beam, area of cross-section of the beam, elastic modulus of the beam. I is the area moment, which is related to width times height cubed divided by 12. Okay? So here's what the problem comes down to. Problem comes down to the following. You see that equation 4, right? It's a transcendental equation, but basically that equation is going to be satisfied for certain values of beta, right? So in other words, the left-hand side, cosine beta L times cosine hyperbolic beta L plus 1, that becomes 0 only for certain discrete values of beta. Okay, there are only certain beta values that will satisfy it. Okay? Each beta, and it's an infinite number of beta values. There's one beta here that satisfies it, another beta somewhere else. Each beta corresponds to a value of omega, natural frequency, and that's how you get all the natural frequencies of the beam. Simply by looking at what are the values of beta that satisfy equation 4. That's it. Right? Every value of beta that satisfies equation 4 gives you the corresponding natural frequency. And so this is how you find out what are all the natural frequencies of the beam. Okay? By simply solving equation 4 for beta values. If you go simply into MATLAB or Mathematica, you'll find out that you'll get many beta values. There's a lowest beta value which corresponds to the lowest frequency, then the second lowest, third lowest, but that keeps going on. There are always a very large number of beta values for which this equation holds, and each beta corresponds to a frequency, a natural frequency. Okay? It just means now that this beam, therefore, supports an infinite number of discrete frequencies at which it has this characteristic shape. It's a resonance, okay? And for every beta value, so in fact, if you do it, you actually get the lowest beta value, beta times L value is 1.875. The second value of beta at which equation 4 is satisfied is 4.69. Third value is this. And remember, beta is connected to, beta is the same, beta, you got beta squared and omega squared, right? So beta is effectively the same as omega, okay? So this is or is there a square missing? I think it should be. Let's just go back to beta fourth. Give me a second here. Oh, I'm sorry. Yeah, sorry. Yeah, this is omega. This is not omega squared. Okay? This is omega. So beta squared goes as omega. Okay, so omega is like beta squared. So if you look at the very first beta, it's 1.875. The second beta is 4.694. So if I look at the ratio, 4.6 divided by 1.875, right? That ratio is what, about between 2 and 3, right? So this tells me that the ratio of beta of the second mode to the first mode is between 2 and 3. That means the ratio of the frequencies between the second mode and the first mode is going to be square of beta, right? Which means the ratio of the second mode to the first mode frequency is going to be, it turns out, somewhere between 6 and 7. So if you just take this ratio, 4.694 divided by 1.875 and square it, that's the ratio of the frequencies of the second mode to the first mode of a beam. Okay? So for every beta value, the corresponding shape is given by this expression. You need to plug in the corresponding beta value and you get a certain shape out of it. Okay? So if you do this, what you get is this. The first eigenmode corresponds to it just moving up and down, where beta L1 is 1.875. The second eigenmode corresponds to what's shown here in the middle, and it has a nodal point in that it bends down and goes back up, has a node, vibration node in the middle. The third eigenmode actually bends up, down, up again. It has 2 vibration nodes. So typically the nth vibration mode has n minus 1 nodes in it of vibration typically. And the frequency ratios of the first mode to the second mode to the third mode then are 1 to 6.26 to 17.55, etc. So what this means is when you take a cantilever chip from a manufacturer and it has a fundamental frequency of 100 kilohertz, let's say, you expect the second mode frequency to be 600 something kilohertz, 6 point something. Okay? So this is important. The key thing is that the frequencies of the second mode to the first, I mean, they don't scale by a factor of 2 or 3. They scale more like in some funny numbers. Frequency of second mode to the first is somewhere between 6 and 7. Frequency of third mode to the first is somewhere between 17 and 18, and so on. Okay? All right. So these are different eigenmodes, and we now know how to calculate the characteristic shapes corresponding to the eigenmodes and so on. Okay? So now let's go back to, gee, this is great, but yes.
Could you just comment about the difference between harmonics and eigenmodes?
Right. So the question is, what's the difference between harmonics and eigenmodes? And it's a very important point. What we just showed is for a cantilevered beam, omega 2, which is the frequency of the second mode, omega 3 is the natural frequency of the third mode. You look at the ratios of the frequencies, 1 to 6.26 to 17.55. Now go back to everything you studied in sophomore physics of string vibrations or vibrations of acoustic columns. Do you remember what the ratios of frequencies used to be? So if you take a string, what's the frequency of the second resonance to the first? Anyone know this? You play guitars, some of you. Maybe you play electric guitars now, so you don't know what strings are like anymore. You got a string, the first mode does this, right? The second mode does this, right? What's the frequency of the second mode to the first mode in a basic string vibration? 2 times. What's the frequency of the third mode corresponding to the first? 3 and 4 and 5. If you do acoustic columns, if you have a semi-open acoustic column, it's 1 to 3 halves to 5 halves or something like that. But there are fixed ratios, right? If it's a completely closed acoustic column, it's 1 to 2 to 3 to 4, 5, and so on, right? So what you clearly see here then is that these frequencies do not scale by 1 to 2 to 3 in beams. They do not behave like strings. So in other words, they're not harmonics. And in other words, they're not good for musical instruments. musical instruments require harmonics. It's very important. That's why musical instruments tend to be more string or membrane-like structures which produce harmonics, whereas things that have bending stiffness are not so good for harmonics. They produce frequencies that are not harmonically related. Okay. It's interesting if you think about it, why stringed instruments and why when you have most drums and stuff and cymbals, drums are basically, these taut membranes also that have these integer frequency relationships. So, interesting. Okay. And it all has to do with the nature of the elastic medium. Here we have something that has bending stiffness. It has a thickness. It's a three-dimensional elastic medium. If you have something that's very thin and under tension, high tension, it starts approaching the 1 to 2 to 3. But if you don't have tension, if you don't have very thin membrane-like structures or string-like structures, then you have this ratio of frequencies. Okay, so the bottom line is this is great. We know how to do this now, but at the end of the day, we do want to retain the simplicity of the point mass model. Okay, so remember, the point mass model, the concept of it was based on the fact that, the whole beam, I'm going to replace it by a spring of the static spring constant and just allow the mass to be the tip mass, right? Now we realize, look, everything's off. We had to throw all that out of the window because now you have to consider this as a continuous beam with its inertia, everything. So how do we get back to the simplicity of the point mass model? So this was sort of very nicely discussed in a paper out here. And what you see out here is, let us say, can someone tell me which mode number is this beam vibrating in? How many nodes do you see? You see 3 nodes. So this must be the 4th eigenmode. Okay? So let's say the cantilever is vibrating in the 4th eigenmode. And this is a true eigenmode shape, right? Where the tip moves up and down Q. Q is the motion of the tip, actual deflection of the tip in nanometers. But you see this thing really wiggling in the 4th mode. The base is being shaken by an amount Y. What we want to do is to replace this very complicated thing by the image on the right. We want to replace it by a point mass, right? The question is, if there's an equivalence, once I choose a certain peak to oscillate in, at that peak, the cantilever is oscillating in a characteristic shape, I want to replace all that by a simple point mass model. And that mass of that oscillator is going to be m sub I, I representing the eigenmode you're driving at. So what it means is, if you choose to drive at the second peak, then I is equal to 2, and there's a certain m and a certain k value corresponding to every peak. That's the key point, right? So when you choose the 3rd eigenmode, i.e. the 3rd resonance peak, the m would be m3 and k3. The stiffness would be spring constant, would be that of the 3rd eigenmode, and so on. So for every peak you choose, there's a different value of k, there's a different value of m. So how do we do this equivalence, right? And so it turns out that the answer is simply to say there's an energy-based equivalence. So if you want, so for example, phi sub I is the eigenmode that it's oscillating in, right, the shape. If you want to know what is the equivalent spring constant for that eigenmode, all you do is you calculate the total strain energy in that eigenmode, which is given by this integral expression. I can share with you the details offline if you want, but in continuum mechanics, you can actually get a whole strain energy involved in that shape as it bends. All you simply do is you equate the strain energy in that shape to the strain energy in the simple point mass model. What's the strain energy in the point mass model? What's the elastic energy stored in a spring? It's 1/2 spring constant times displacement squared. That's it. So all you do is you take that shape, evaluate this integral, and simply ask the question, what should this number ki be in order for the energies to be the same? If the strain energies in the point mass model and the continuous beam model are identical, then you have identified the correct k. Okay, so that's how you get the correct k, spring constant value, for the point mass model. Similarly, if you want to know what is the correct point mass, value of the mass of this oscillator to put in, you equate the kinetic energy of this oscillating beam, which is shown here. It's the integral rho a phi I squared dx. It's basically the kinetic energy. You equate the kinetic energy to that of the point mass oscillator, the kinetic energy of the point mass model oscillator is 1/2 mq squared, correct? Q is the tip displacement. That's it. So what is the value of m for which the kinetic energy of this continuous beam models matches with that of a point mass oscillator? That's it. If you do it correctly, very interestingly, this is the result you get when there is no tip mass. Remember, all these eigenmode shapes I calculated in the previous slide were assuming the tip mass was 0, which fed into the boundary conditions, right? Retaining that assumption, you actually find that the spring constant of the first mode is actually 1.03 times the static spring constant. That is, if you apply a point force, what the resistance is when it bends up, it's actually 1.3% greater than that. Okay? This reflects the fact that when you're driving in the fundamental mode, the shape in which it oscillates is not that simple cubic curve. Now you know it's this sine hyperbolic, cosine hyperbolic, and so on. The shape is slightly different. If the shape is different, energy gets slightly different. If you choose to drive the second eigenmode, the spring constant is 40 times that of K. If you choose to drive the third eigenmode, it's 317 times K. All these numbers work out by doing the integral using the mode shapes showed on the previous 2 slides. So what it means effectively is when you've got a beam, you've got many eigenmodes, right? As we discussed, at different frequencies. When you choose to drive it at one particular peak, you effectively got an oscillator with a certain spring constant and a certain Q factor. You choose to drive it at a second mode, you have a completely different spring constant, completely different Q. At the third mode, completely different K, completely different Q. So really, when you have a particular beam, you don't have one point mass oscillator, you have many with different K and Q values, and it's not one tool, therefore you have, but you have multiple oscillators. You can choose which one you want to probe your sample with by choosing the frequency at which you're driving it. That's a big result, important result to convey to you. All right. The interesting thing, though, is in this analysis, the mass of this oscillator, regardless of the mode you're in, is the same. So as you go to higher modes, the equivalent mass that establishes this equivalent does not change. It's only the stiffness that changes. Okay. So the details are shown in this paper. Now, remember, in all this discussion, I neglected tip mass. The question is, what happens if you do include tip mass? I'm sure you now know that you would have to go back to the equations and modify the boundary conditions for it, because our boundary conditions at x equal to L did not have any tip mass included. If we start including the tip mass, it turns out it does not change the shape of the first eigenmode much. But the second eigenmode shape starts changing when you had a tip mass, okay? And what ends up happening is the nodal position starts changing and so on. The key thing is that when you have a tip mass, the spring constant of the second mode is not 40 times that of the static spring constant. It comes out to somewhere between 60 to 80 times because of this effective tip, okay? So and all AFM cantilevers have a tip. Otherwise, it's not a probe, right? So in reality, the spring constant of the second mode is often between 60 to 80 times of the first, not the 40 that the simple theory without tip mass would suggest. Okay? Okay. Many of you are going to use cantilevers that look like this. These are triangular cantilevers. Many of you use these cantilevers also. What happens to this whole eigenmode picture when you have these kind of cantilevers? Of course, on the very top you see what one would consider a first bending mode. On the bottom left you see what would be the second bending mode of these triangular cantilevers. But the interesting thing, not surprisingly, is you can regard these things as two cantilevers that are joined together at the free end, not a single one, right? You can think of them as two separate ones. And if you have two separate ones, you also have the possibility not only to have both going up and down at the same time, you also have the possibility that they do this. And if you look at it, what you end up getting is, for these kind of cantilevers, the eigenmodes are not, the frequencies are not spaced at 1 to 6 to 17. They're not spaced like that. It turns out you have this, the first bending mode, both go up and down. Slightly above that frequency, you have another resonance where they're going out of phase and they're twisting it. So the eigenmode frequency in the top left and the eigenmode frequency in the top right are actually not far from each other. They're pretty close. It's interesting. I mean, it's not like very far apart. Now you look at this one at the bottom left, and there's a second mode. And just like there's a second mode, there's out of phase second mode. This is the both beams are oscillating in second mode, but out of phase, causing a twisting-like motion. And even this frequency is different. It's not the same frequency relationship as we had, okay? All right. Nonetheless, complicated as these mode shapes are, the idea of the point mass equivalence always holds. Once you choose a certain resonance peak to operate in, there's a specific K and a specific Q that corresponds to it, okay? So you don't have to, you can worry about these details, but at the end of the day, the good news is you can always replace all this stuff by a single point mass model. You just have to be careful in what K value do you use for it. You cannot use the static spring constant, that's all. Okay, so we're going to start talking a little bit about phase contrast now, and in particular analytical approaches to doing this. Remember, we have done Veda. You know how to do simulations with Veda. You can track phase and amplitude as you approach a sample. You can see how those values change depending on the interaction parameters. But we want to have always some analytical closed form expressions because they're very easy to, if there's a closed form expression, you know what you're doing. It's much nicer, right? So can we do anything in AFM that gives us some important closed form relationships? The first most important analytical result in dynamic AFM and tapping mode AFM relates what is called the phase contrast to tip sample interaction properties, okay? And we're going to study that now, okay? So what we're going to do is we're going to go back to the point mass model, but use the correct K value and the correct Q value based on this equivalence that we just did, okay? But before we do that, let's talk a little bit about phase contrast, okay? The idea of phase contrast is simply that you're looking at a drive signal that's going into the piezo that's shaking the cantilever, correct? That is shown by the dotted sinusoidal wave. That's the drive signal to the cantilever. What you're measuring out of the photodiode is the solid blue or green line. That's the sine wave you get that you're measuring, right? So you got two sine waves. One sine wave goes in, is the excitation, the dotted line. The output is the solid line, is what you're measuring. There's a phase difference between the two, right? So there's a phase difference effectively between the shaking and the response of the tip that you observe. And from the early days of atomic for dynamic AFM, it was recognized that as you scan a surface, in tapping mode, you're keeping the amplitude constant. Therefore, the phase can change over the sample depending on local properties. So the very first idea of going beyond topography in AFM came with this idea of phase contrast. They said, well, you can do topography, but hey, you can also monitor how the phase changes over the sample. And maybe if you make a map of that, you get really important information about the composition. So the very first channel in AFM, in dynamic AFM, that was used to map compositional contrast was phase imaging. So for example, here, this is from Vico's, now Brooker's website. On the left, you see topography image of this polymer system where you have these spherical bumps effectively. And, you see something, but when you look at the phase image, you just see really nice contrast and properties, okay? So from the early days, it was recognized that there was a channel available to us in AFM for mapping properties of a surface along with topography. So not surprisingly, it became one of the big areas of research because, hey, there's only so much you can do with topography. Always you want to know more about your sample, right? You want to know more. You want to know how sticky it is, how bouncy it is, how soft it is, and so on. So this is the channel that offers you that possibility, right, of mapping properties. So the question is going to be, really, what does it mean? And so this goes back to some classic work in the late 90s, where this is work out of Ansikowski et al., Bernd Gottsman, Ansikowski, and then later Ricardo Garcia and a few other people who tried to set up a basic theory to help understand what we get these contrast images. What do they mean? What would it mean? So we are going to study this using an analytical model. So here we are. We have a point mass model. And remember now that the spring constant here, K, is going to be the spring constant of that particular mode. Okay, so I hope I've explained to you that in spite of the complications of this extended nature of this beam, at the end of the day, you can, if you choose the correct spring constant, choose the correct Q factor, you can use the point mass model without a problem. Okay, so we're going to do that. So here is our point mass model, X, and I apologize for the switching between notations because in the continuous beam model, X referred to the X-axis. Now X refers to the tip motion up and down. I apologize for the switch in terminology, but with point mass model, we've always been using X, so we'll stick with that. So here's the motion. D is the gap between the tip and the sample, which is Z plus X. X is basically the deflection up and down of the tip. Z is the separation, separation between the base of the cantilever and the substrate. So our equations of motion are shown on the very top, mx double dot. M is the mass of the oscillator. Now remember, it's not the tip mass. It is the correct equivalent mass as described in the previous 2-3 slides for that eigenmode, okay? Equals negative kx. Again, k is not the static spring constant anymore. K is now the equivalent spring constant of that eigenmode. X minus cx dot, which is just some damping due to the air, let's say, equals the force applied on the cantilever. It could be from base motion, it could be from magnetic excitation. It's simply a harmonic force, F0 cosine omega t, right? And the tip sample interaction force is FTS, and that depends on the tip sample gap, right? Correct? And it depends on possibly tip sample velocity, because maybe the interaction is viscoelastic. If the interaction is viscoelastic, then the tip sample force will depend on the rate of indentation, right? Remember, when D becomes negative, we have indentation. And so as soon as you have a tip sample interaction force that depends on the rate of indentation, it means it's a rate dependent interaction law, which could come from viscoelasticity, it could come from plasticity, all sorts of sources of it. Okay? Okay, so this is our equation. How are we going to use simple analytical understanding to get to phase contrast? Here's what we do. In equation 1, what I've done is I've divided everything by K. I've divided the entire equation by K, the spring constant, and define omega 0 as the natural frequency of this oscillator, square root K over M. Again, K is going to be the equivalent spring constant for that eigenmode. M is the equivalent mass for that eigenmode. Okay, so this applies for whichever eigenmode you choose. Okay, this is no longer the simplistic point mass model. This is now the equivalent point mass model. Okay, Q is the Q factor of the oscillator that you now know what it means. So here's what we do. We assume that the tip also oscillates harmonically with an amplitude A. X is going to be A cosine omega t minus phi. Okay? So x dot, which is the velocity of the tip, is going to be the same as d dot, which is the rate of change of the gap, is going to be negative A omega sine omega t minus phi. Now remember, I've chosen the solution to be A cosine omega t minus phi, okay? Which means that phi is the phase lag. It's not the phase lead, it's the phase lag, okay? Very important distinction. You need to be very careful in your AFM analysis about whether your AFM system plots phase lead or phase lag, because interpretation flips depending on what you do. Here I've defined phi as a phase lag because many AFM systems actually have it plotted as phase lag. A is the set point amplitude. A is the amplitude at which you're scanning. There's the amplitude at which you're scanning, which of course, if you keep it at volts, you don't know what it means. Okay, so I hope you know how to do the conversion of volts to nanometers, and any image you take, you say that this is taken at, 5 nanometer set point amplitude or something. I hope that's very clear now, okay? So what we do is we substitute 2 into 1, into equation 1. That's all I've done. I've just substituted 2 into 1, okay? And what we get is equation 3. Okay? Everyone with me so far? Yes?
As an experimentalist, when you measure the phase in your AFM system, what is the simplest way you can, simplest technique you can use to determine whether the system is giving you the phase lead?
Okay, very, very good question.
Simplest experiment you can do this.
Okay, it's a very, very, very important thing. Okay, very good question. So how, as an experimentalist, do you know whether your AFM system gives you phase lead or phase lag? It's very important because it's very important. So it's, the easiest thing, in my opinion, to do is simply to plot, do a tuning curve. So you withdraw from the surface, do a tuning curve about that resonance, and you plot A versus frequency, right? And you get this resonance curve, which you want to operate on. While you do it, make sure you plot the phase, or whatever they call the phase. And nobody tells you that it's a phase lead or phase lag. They're just going to say phase, right? That's all they're going to say. You plot that. And if you find that it does this, right? That is, whatever number it's plotting, hopefully it's in degrees, okay? If it's in volts, again, I'm going to get very annoyed with you guys showing me these things in volts, okay? So degrees, make sure it's in degrees. Luckily, all new AFM systems automatically do it in degrees. The older ones, even the phase would be in volts, so terrible. Trying to convert that into degrees would be terrible. If it does this, what do you think it is? It's a phase lag or phase lead? Going back, you know, we have studied these resonance curves before. This would be phase lag, because what it means is when you're far below resonance, it's lagging very little. And when you're above resonance, it's lagging by a large amount. So what it means is when the lag, so it's going to be the phase lag that increases across resonance. On the other hand, so this would be lag. On the other hand, if the tuning curve does this, something like this, right? Then it'll be phase lead, right? And it'll be typically a negative value. And it'll get more and more negative. So just by looking at the shape, you can tell if it's plotting phase lead or phase lag. That's the easiest way I would suggest to check. So in other words, you know, we use the fact that we know theoretically when you're withdrawn from a surface, you do a tuning curve. I've shown you the transfer functions. You know that. You know how it should behave. And so see what you get, and based on that, judge if it's lead or lag.
So when the AFM company plots the phase in degrees, it can be shifted.
Yeah, oh yeah, that's completely true. That's why I did not show any number on here. And so usually, so the first thing you do is to look at the generic shape. Does it go down or up across resonance? If it goes up across resonance, it's phase lag. If it goes down, it's phase lead. Another important thing, as Ron just pointed out, is often you have to center the phase. Whatever it is, often you have to center the phase. And at the peak, you have to sort of click on this curve and make this point equal to 90 degrees. Or minus 90 degrees if it's phase lag, you would call this point 90 degrees. If it's phase lead, you would call this minus 90 degrees. Because at resonance, the oscillator is lagging behind 90 degrees. So if you're plotting lead, it'll be negative 90 degrees. Okay? See what I'm saying? That's why lag is nice, because lag is always a positive number. Right? Okay, so you do have to center it just to make sure everything makes sense. Okay. So we're at equation 3. Let's go to the next slide. And in the next slide, I've repeated equation 1 and 2 from the previous slide, okay? So the assumption is x is a cosine omega t minus phi, a is the set point amplitude, phi is the phase lag. And this velocity, I've carried that equation over, okay? The last equation from the previous slide. Now here's what we're going to do now. We're going to multiply both sides of the equation by sine omega t minus phi. You see that? And we're going to integrate from 0 to 2 pi over omega. 2 pi over omega is the time period of the drive cycle, okay? You're driving with frequency omega, so the time period of that drive signal is going to be 2 pi over omega. So I multiply both sides by sine omega t minus phi. In your homework problem, you'll be asked to do this. So do pay some attention to this, how this happens. So if I multiply that whole equation by sine omega t and integrate, let's look at the very first term. The very first term involves cosine omega t minus phi, okay? You see the first term is cosine omega t minus phi. Everyone see that? If I multiply that by sine omega t minus phi, I'm going to get sine times cosine of the same argument. Sine times cosine of the same argument is sine 2 theta effectively divided by 2. If you integrate that over 0 to time period, you're going to get 0. Okay? So it turns out that when you multiply by sine omega t minus phi, the first term goes to 0. The second term is non-zero because now you're multiplying sine omega t minus phi to itself. You get sine squared. Whenever you get sine squared and integrate, you get a non-zero term out of it. So when you do that, when you multiply through by sine omega t minus phi, you get the following. You get the negative omega over omega 0 q times pi over omega equals this quantity on the right-hand side. You can rearrange that a little bit and write the expression for sine of phi as Ka over F0. F0 is the magnitude of the forcing times omega over, in curly brackets, omega over q omega 0 minus 1 over pi k squared times the integral. Now, if you think about that integral term, okay, think a little bit about the term inside the integral. The quantity negative a omega sine omega t minus phi. What is that? Negative a omega sine omega t minus phi. If you think about it from equation 1, it's the tip velocity. Everyone with me? So that integral term is basically tip velocity times the interaction force. Everyone with me? So integral contains the tip sample interaction force FTS multiplied by a omega times sine omega t minus phi. A omega times sine omega t minus phi is the tip velocity. Okay? You see that on the very top? X dot, tip velocity. That's what it is. Right? So what is force times velocity? It's power, right? Force times velocity is power. Rate of doing work, effectively, is power. So that term in the integral is basically telling us, and when you integrate power over an oscillation cycle, it's total work done. So what that integral term is doing is it's telling you about what is the work done by the tip sample interaction force on the cantilever. Okay? Now, if the tip sample interaction force were purely conservative, what does conservative mean? It means that if FTS is only a function of distance, d, not a function of rate, there's no rate dependence in it. If that's the case, what do you expect this integral to be? In a cycle, if you have a cycle, you have a conservative force, you go in a cycle, you come back to the same state, it does zero net work. Okay? So that entire term in the integral is actually the net work done due to dissipative forces, or it's the energy lost due to dissipative forces in one cycle of operation. Because if the interaction forces are purely conservative, that integral must be zero. Because you do in one cycle of operation, it has to be zero. Okay? So we can replace that entire integral by a quantity we call E sub dis. This is the energy dissipated in one cycle of oscillation by the tip sample interaction forces, due to the presence of tip sample interaction forces. That's what it is, okay? It's a very powerful thing because we can actually compute as you tap on a sample, as you do a scan, we'll show you how you can actually map exactly in one cycle of oscillation as the tip went and tapped on a sample, how much energy did it lose? How many electron volts of energy? Because these are tiny oscillators interacting. After all, the interactions are between a few hundred atoms here and a few hundred atoms there. We're simply literally mapping out, when this happens, how much energy was lost. It's amazing. It's the smallest energy loss thing that you can mechanically measure if you think about it. Right? So all of us know how to measure energy. We take a ball, due to contact, we take a ball, let it go, it bounces, it doesn't fall, go back to the same height. You've lost energy in the impact, right? That's with the tennis ball, let's say. This is the smallest mechanical ball that it's tapping, moving away, and you measure the loss due to the interaction between a few hundred atoms and a few hundred atoms on the sample. It's amazing if you think about it, all right? That's the EDIS, energy lost to the sample in one cycle of oscillation. So we're at equation 3. Now, we make use of a relationship that we had from before, in that, what is the driving force F0? Okay? How do you know what the driving force F0 is? Well, you've done a tuning curve, right? So you know the tuning curve, and you know that when you're far from a sample, you've done this tuning curve, and you've chosen to drive it at resonance with an initial amplitude A0, right? A0 is the initial amplitude, or sometimes people call it free amplitude. So we know that if you know this amplitude A0, then we know what force you're applying, because we have done the transfer function before. Remember, if you look at the magnetically excited transfer function, it relates the amplitude you get to the driving force. You can invert that, and you can get the driving force F0 in terms of the drive frequency and so on as shown. So Ka0 or F0 comes from that analysis, okay, that we did without tip-sample interaction forces. Okay? So if you know the oscillation amplitude A0, when there are no interaction forces, you can back out what is the drive force F0. So we plug that in, and we get the first of equation 4 that tells you what is the sign of the phase lag. Phi is the phase lag. All this in terms of energy dissipation per cycle EDIS. Life simplifies when you choose to do all your experiments at resonance, like hopefully most of you do this. So omega is equal to omega 0. Life simplifies to this very simple expression, very elegant expression, very important expression. Sine of phi equals A over A0 minus Q pi K A0 times E dissipation. Okay, it tells you that the sign of the phase lag is connected to this. Now, when you're tapping on a sample, and you're scanning a sample in tapping mode, what do you keep constant? You keep the amplitude constant, right? What happens to A0? What is A0? Remember? A0 is the free amplitude, the initial amplitude before you interact. So you got an amplitude A0 before you interact with the sample, and then you interact with the sample, the amplitude reduces to A. So A0, is what we call the free amplitude or the initial amplitude, right? Before interaction. And then A is the amplitude to which it's reduced to as it's interacting with the sample. So when you scan over a sample, A over A0 is kept constant, because you're using feedback to keep A over A0 constant. So if your feedback is correctly set, and if error maps are very nice and flat, very little error due to feedback, then in that case, as you scan over a sample, regardless of the local material properties of the sample, A over A0 must be constant, so long as your feedback control is correct, is operating correctly. Which means that if you see contrasts in sign of phase over the sample, they must be due to different E-dis, E-dissipation. Okay? Everyone with me on that? Okay? So, wherever the sign of phase decreases, sign of phase lag decreases, that corresponds to increased E-dis. Okay? This is why I'm saying it's extremely important that you know whether your system plots phase lag or phase lead. Because if you get contrasts in sign of phase, and you get more sign phase is larger in one place, you're left doubting if it means that the energy dissipation is greater on this sample or less on the other. You don't know whether it's larger or less if you don't know that what you're plotting is phase lag or phase lead. That's the problem. Okay? So if you're being correct about it and you're plotting phase lag, then sign of phase lag is going to be connected to energy dissipation in the following fashion. Beautiful result. Absolutely beautiful result. It was done using a different technique in the original paper by Ansikowski. This method that I've got here follows more along the derivation from Garcia's group. So it's wonderful. This is a wonderful thing, okay? Sine of phase is basically giving you energy dissipation over sample. Fantastic. Energy dissipation between a few hundred atoms as they, quickly approach and move away. Amazing, if you think about it. I still get, excited by the very thought that you can measure. And these numbers are typically in air, a few electron volts. It's just amazing, it's really remarkable. Or picojoules, if you like, mechanically thinking about it. Conversely, you can invert this relationship to get E dissipation, which means that if you have a map of phi over the sample, you can convert that to the actual quantitative energy dissipated in electron volts or picojoules as you're tapping per cycle. Can you believe that? It's an unbelievable thing, but you can do this. Is this relationship E dis equals that? All you need to know for this is you've got your map, you've taken your image, you just need to process the data, you know the amplitude, you know A0, you know phi, you just need to combine this. You can do this in most image processing software. If you've got a map of A, you got a map of A0, you got a map of phi, how do you combine the maps to get a map of E dissipated in numbers, in electron volts, in picojoules over the sample surface? Beautiful stuff, I just find it amazing. These are really small numbers for mechanical energy losses, yeah.
So the dissipation is given by, because I am breaking like a bond. What is that dissipation?
Where does it come from? Yeah.
It's the bond that I am breaking.
Yeah, so yes, the dissipation, well, it depends on the sample. In some cases, if you're doing it on polymers, it could also be some viscoelastic. In the small interactions, you're making chains slide relative to each other. Mostly, though, it is actually hysteretic interactions due to either water meniscus making and breaking or due to tip atoms assembling and ripping apart. So, really cool stuff. But there is another part which most people neglect. All right? Most standard AFM theory just multiplies by cosine and gets done with it. You could also take the same equations and multiply by cosine omega t minus phi. You see, the previous slide, I multiplied by sine omega t minus phi. Now I multiply by cosine omega t minus phi. Very important result also. I want to leave you with this, okay? So give me 2 minutes to wrap this up. If you walk through this, you actually find a really remarkable result, which is cosine of phi equals Ka over F0 times this omega 0 squared minus 1. But look at the term in the integral here. The term in the integral here is F times A cosine omega t minus phi. Now, what's A cosine omega t minus phi? Is the tip motion, x, right? The tip motion is A cosine omega t minus phi. So the term in the integral now simply becomes F times tip position integrated over oscillation cycle. All right? And it's integrated from 0 to 2 pi over omega, so I can, take the average value of that over the cycle. That quantity in pointy brackets is basically tip sample interaction force times position integrated over the cycle. So that does not have any interpretation of power, because now we're talking of force times position. No, it's not work anymore. It's force times position, not even displacement. It's just force. What is the tip sample force as a function of position and back? That's all. This is a different quantity completely, and it's called the virial. It's called the virial. Okay. It turns out that this number, this virial, is only dependent on conservative interactions. Dissipative interactions don't make any difference to this number. So what you find from this analysis is when you choose to drive at resonance, cosine of phase gives you the virial of the tip sample interaction force, which is the measure of the conservative part. Okay, this is a very spectacular, let's say the left hand or the evil cousin of phase contrast. Everybody, the standard derivation you see is with respect to sine of phase, right? But you look at the cosine of phase, it's the twin. It's the evil twin, so to speak, that exists, and people don't know what to do and how to deal with this. Okay. What this means is, when you take a phase contrast image, you cannot just directly say, oh, this is dissipation. If you plot sine of phase, what you're doing is measuring energy dissipation. If you plot cosine of phase, you're actually plotting conservative interactions, a measure of conservative interactions, Van Waals forces, elasticity, etc. Hardly anyone makes this distinction, but it's very important. Not surprisingly, if you get a contrast in phase, if the value of phi changes over the sample, obviously sine of phi and cosine of phi are also going to change over the sample. Okay? So, last comments in phase. Number one, pay attention to whether your system plots phase lead or phase lag. Thanks to Ron's question, pointed that out. Always make sure to plot phase in degrees, never in volts. Phase cannot be in volts. It cannot be, all right? It's only when you map sine of phi over a sample, not phi, it's only when you map sine of phi that you can correlate the numbers to energy dissipation. Okay? Specifically, if you go back to this relationship, up here, sine of phi equaling this, right? If I brought A over A0 on the left-hand side, so it's sine of phase minus A over A0 would be directly proportional to energy dissipation, okay? So, if I truly plot not just phase phi, not just the phase lag phi, but sine of the phase lag minus the set point ratio, which is A over A0, that quantity, if it's double value at some place corresponding to another place, that means that the energy dissipation is double compared to here. That's how you can start making quantitative, comparisons of energy dissipation. Is it double or half? If you just do phase lag, you won't know. You do sine of phase minus the set point ratio, then you know. Wherever you get double that number, it means it's double the dissipation. Okay? When you plot cosine of phi, it's a map of local conservative interactions. And that also you get contrast So, the question, for a long time people will say, oh my God, so what is phase telling you? Is it telling you this or that? Is it conservative, dissipative interactions? The answer is, if you do sine of phase, it's dissipative. If you do cosine, it's conservative. Which means you actually have both pieces of information. So, in a way, what happens is, as the oscillator oscillates in interaction with the sample, it chooses a value of phase lag, which sort of balances the conservative and dissipative terms so that the sine and cosine terms adjust themselves in a way, in the appropriate way, basically. Okay? So, having said that, I will add one more thing. When you do phase contrast in liquids, even the interpretation of sine of phase changes. So right now in air and vacuum, sine of phase is dissipation, cosine of phase is the virial, conservative virial. But in water, even the sine of phase changes. Okay, so let me quick show you one last example. This is from a review article from Garcia et al. In Nature Materials. On the top left is example of a bacterium that's actually coated with a polymer. And you see a topography image of it. So you don't see the actual structure of the flagella inside it. However, you do phase imaging and you see the structure. Now, I want you to be critical about this image. The phase image. Do you know if it's phase lag or phase lead? Nobody knows. It's just contrast, just thrown out there. Nobody knows if it's phase lag or phase lead. Is it energy dissipation? No, it's not, because they haven't plotted sine of the phase lag, right? So you cannot say that just by looking at this, if the darker parts are more energy dissipation or less energy dissipation. This is the problem. See contrast, but to extend the physics to get an idea where is there more or less, you need to be sure you're dealing with phase lag. You need to plot sine of phase and so on. Okay. So with that, do you have a question?
So yeah, on the idea of phase lead per se, the sine of phase lead also equal energy dissipation, or is that a different?
There's a negative term. You just have to account for if it's lag, lead, you just put a negative, but then it switches when phase is less or more. That's why it's a problem. Okay, so please read Garcia and Perez, the reader. It's got very nice. Some of the analytical results are given there. We'll continue with these analytical results in the next class. Okay, and on Friday we have a makeup class. It's in room ME 116 on Friday 10:30, same time. I'll send you an email. Yeah. Thank you.